So I hope you saw that, I hope you read an announcement that I sent today. It's about moving your test by half an hour later, the test 3. Let me share the screen, share screen. All right, so it's this announcement here. So it's important one, so please take note that the test, due to the conflict that many students have with their physics midterm, is moved by half an hour. So it's going to start, the day didn't change or anything. Really, the difference is just in 30 minutes. So it's going to start at 12:30 instead of 12 on Saturday, 21st. So not this Saturday, but the Saturday next week. And you're going to have 15 more minutes than you had in previous tests. So the test is ending at 2:15. And as usual, you're going to have 15 minutes to submit. So the server will close, submission server will close at 2:30. All right, so before we start the lecture, are there any questions? Hey, and so, yeah, don't forget that the test is starting half an hour later. Okay, Mait, can you put your hand down just so I can notice when somebody new puts when there are new questions? All right, thank you. All right, so let's start with today's lecture. So what I want to show you first, so let's go to Python and let me create a list. It's going to be a list of about 1,000 elements, random elements. One of the useful questions in useful function in a random module is called sample. It basically, from a sequence or from a set of elements, it picks a random number of elements. It samples basically random elements from a sequence, and you get to say how many elements do you want. So it basically takes 2 arguments. First one is the sequence that you want, and the second one, how many elements you want to sample from that sequence, so you get a random list at the end. So for example, you can say my sequence is the one produced by a range function, and I want numbers from 1 to million. So 1, 2, 3, 1, 2, 3, but the last one is 1. So we are going up to 1,000,001. So the numbers here are from 1 to million. And I say pick 1,000 elements from there at random. Okay, so this random sample function is going to pick 1,000 elements in the range of 1 to million, and it's going to return a list with such elements. So let's see that. So what's stored in L is a list of 1,000 random numbers from 1 to million. And there's something that we're using throughout the semester, which is if you wanted to know if number 50 is in a list, for example, you would do a 50 in L. So you were using this operator in L many times throughout the semester. So you should all be very familiar with it. And it turns out, for example, the 50 is not there. Okay, it's not a surprise. The probability is not very high that 50 is there. 1,000 elements from 1,000,000 was picked. Okay, so 50 is not there. What about, I don't know, I can pick some number that I know is there. This one here, we can ask, is it in L? And then Python tells us that it's searching for that number, tells us that the element is there. A similar function, actually, a function that searches through the list looking for a given value, there are 2 implementations of it in Python. And the second one is in list module. The function is called index, and it's actually a method. So you use it, you call it in object-oriented way. So if we want to call this index function that is doing searching in a list L, you do list.index. So name of the method is index. And as an argument, you give it a value that you're looking for. So, for example, we know that this value is in the list. The difference is that not only do you find out with this index method, not only do you find out that the element is there, this function also returns the first position where it finds this element. So you find a little bit more, not only that the element is there, if it's there, you also find where it is in the list. And that sometimes you may need that for whatever you're trying to do. All right, so this tells us that this particular element exists in list L and it's in position 4, 8, 9 in the list. Okay, index method, if an element is not there, like our 50, like value 450, it's going to throw an exception, basically letting you know that you have a value error of 550 is not in the list, but now that you have seen try and accept, you know how to handle it. So if you want to use index method, you can use it and use try and accept to handle the situation when a particular element is not, that you're looking for is not in the list. So this is all to tell you that in search, for example, searching for a particular value in a list, you have 2 implementations in Python, and that's not a surprise. It would be easy to argue that it's basically the most fundamental problem in all of computer science is searching for values, searching for something, okay? So let's first understand what type of solution, what type of algorithm is actually used when implementing this in and when implementing this index. Okay, it's an easy algorithm. Some version of that algorithm we implemented in many ways during the semester. Let me show you a few slides. So what is the problem that we want to solve given a list or given a sequence and given some value? I want to find out, is the given value in the list? Okay, so let's look at some slides, and the easiest solution and first thing that comes to mind, and as I said, something in one way or another we implemented many times, is you have a certain value that you're looking for. You go through the elements of list one by one, you compare it to the value you're looking for. If they're the same, you can stop and return true. Otherwise, you take the next element of the list, compare it to the value. If they're the same, you report it. If they're not, you take to the next element, and so on until you come to the end of the list. So through this process, either you find the value in the list or you come to the end of the list and realize there's no more possible places to check and the value is not there. You report that the particular value is not there. So this super simple algorithm is so fundamental and so much in use that even has a name. It's called linear search. And probably the reason that it's called linear search is that you're going like on a line, you're going from left to right linearly through the elements of the list one by one. Although surely everybody understands this, let's look at a little animation of how linear search works. A common word for value that you're looking for is a key. You're looking for a key. So you will find both words, value or key. It's what you're looking for. And a list is a sequence through which you're going through. So for example, we are looking for a value 3, a key 3 in this list. So you're comparing first that value to the first element of the list. They're not the same. You compare it to the next element of the list. It's 4 here. They're not the same. Next one, they're not the same. Next one, 4th one in the list, they're not the same. 5th one in the list, they're not the same. 6th one in the list, bingo, they're the same. So you can report true, we find the element in the list. Or if you want the implementation that reports the position, you would now report it's in position 0, 1, 2, 3, 4, 5. It's in position 5. All right, so that's a linear search. It's super simple. It's equally simple to implement. So let's just do it quickly just for the completeness sake. So, and so we can analyze how good is this solution. Okay, so we have linear search. It's the name of a function. What we're given is some list and some values that I'm going to represent by a parameter v, a variable v. And I want to find out, is this value L? So this is linear search, this is list, and L is a list. V can be any object if you like. A list can be list of anything. And what you want to return, let's say we want to implement that, we want an implementation that returns a position where we found the element. So in that case, we're returning an integer because position in the lists are integers. Okay, so we know how to implement this. Let me see that I did it the same. I'm going to, as usual, call the size of the list n. I'll even use it just because we're going to analyze how good this solution is. So let's loop through the positions, because in case we find an element, we want to return the position of that element for I in range n, because n is len of n. If L in position I, so the current element we're looking for, is it equal to the value we're looking for, we just return the position where we found that element. Okay, so if we go through this whole list and never return a value, because remember, first time you return the value, the function terminates, it means you found it. If this is never executed, if we never found this value and we found ourselves outside of the loop, it means we went through all the elements of the list, we didn't find the value. So what should we return? The convention in this case is to return -1, because position -1 doesn't really exist in the list. Although in Python, -1 is interpreted as the second to last one, but forget that. For now, we are just saying, if I return -1, that means that your element is not in the list. Okay, so there is your implementation of linear search. And basically, both in operator and index operator implement this algorithm, so linear search. Except that in one case, in case of in, it's just returning true or false, and in case of index, it's returning a position where it finds the element. Okay, so how many operations does this solution do? So you have a list, it can have million elements, it can have billion elements, so n can be a big number. How many operations does linear search take? In terms of big O notation. This is O of what?
O of n.
This is O of n, exactly. So this does a linear number operation. This is one operation, it's not even a part of this. The loop is executed. This for loop is executed n times. Each time you execute, a single value is assigned to variable I. So that's one operation. So this line costs you n operations. This line is executed n times, and each time you're just comparing two values. So you're doing one operation each time you execute it, and you do it n times. So this is n, this is executed one time, this is executed one time at most. So we do at most, so less than equal. What we want to do, I want to guarantee that the number of operations is what when I say big O of n, it means I'm guaranteeing it's at most this many operations. So this is 2n plus 3 at most, and we say remove the constants 2 and 3, and you end up with linear. Okay, so we have a linear solution. All right, so let's keep this. This is a linear solution. So if you have a list of billion elements and you're looking for some value, it's going to take you about billion operations at least to solve this, especially if the element is not there. Okay, if you're lucky, maybe the first element is. We're talking about the worst case. We're talking about in the worst case, no matter what you give me, if I have a list of size n, I'm guaranteeing you that this solution is going to do roughly n operations. Okay. So let's understand what problem we solved. We solved a problem where given any kind of list, you don't know anything about this list, and you're looking for some value, your solution finds out if that value is there or not. Can this be done better? Can you improve on O of n? Can you do it faster than O of n, faster than linear number of operations? What do you think?
No.
Why?
Because we wouldn't be doing 1n, so we would be skipping.
Right, exactly. If you don't know anything about the list, possible to skip a single element. What do I mean by that? Just reading, if you have million elements and you're looking, is 50 there, okay? Just reading million elements, meaning looking at million elements, right? If you're going to compare it to 50, you have to read that element. Reading every single element in the list is going to cost you n operations if the list has n elements, okay? Reading a single element of the list, that's one operation. Okay, so if you have n elements, let's say I have a solution, you claim that you have a solution, you don't know anything about the list, you claim about that you have a solution that takes less than n operations. Let's even say n minus 1, but that's not possible because looking at all of the n elements cost you at least n operations. So if your solution is doing n minus 1 operation or less, it means there is at least one element in the list that you didn't read, that you didn't look at. How do you know that that's not 50? So you may give incorrect answer. So there is no better algorithm. If you don't know anything about the list, there is no faster algorithm than linear search, okay, than linear. Well, this is a linear algorithm, and the name of the solution algorithm is called linear search, although I don't think it's called linear search because it takes linear number of operation. It's probably called linear number of search because you go linearly through all the elements of the list. It's just a guess. All right, Lilia, what's your question?
Maybe we can sort the list.
But how many operations is sorting?
Log n?
No. Sorting is n times log n. In order to sort, but think of it this way. I asked you to take as a black box that sorting takes n log n time because we haven't got to sorting yet. But even if you forget, log n is much less than n. And in order to sort something, you at least have to read each element once. So it's at least n. It cannot possibly be, you cannot possibly sort something without reading every single element once and then starting sorting, right? So the fastest sorting algorithm that exists and that it can exist is big O of n log n. So if your solution, yes, it would be great if the data is sorted, okay? But if it's not sorted already, the step number 1 of sorting is going to cost you more than this because n times log n, you're looking at n times log n versus n times 1. So you're comparing 1 to log n. Log n is a slow growing function, but it's still faster than, 1 is not growing. Log n is growing with n, okay? So log n is more operations than n, right? So your solution cannot start with sorting in this particular, it can, but then it's not a better algorithm. It's not a faster algorithm. Okay, so if you don't know anything about your data, then you cannot do better than linear search. This is the best possible algorithm for that. All right, but then, as was suggested, although the suggestion was to sort first, we cannot afford to sort. What we can afford and what almost every reasonable application on the planet does is keep your data sorted, okay? So from now on, you should always, if you're working with some data, your data should be sorted to begin with. You keep your data sorted. So the question then is, can we do better if we know something about the list? Such as, is there a better solution if the data is sorted already? Okay, so you know something about the list. We want to design a solution. I'm going to give it a name. So what we want is, let's look at the slides actually on this before we code anything. Not this. All right, so what we want is, all right, we know that if we don't know anything about data, linear search is the best we can do, and we pretty much know everything there is to know about it by now. Okay. All right. So what if you know something about the data? What if the data is sorted already? Okay, so you're working with a sorted list. Something gives you a value like this list here. We have a list of how many elements? I can't seem to see my screen. There it is. We are looking at a list with 17 elements. So the elements are 2, 3, 4, 9, 18, 39. You can see that the list is sorted. And let's say you need to find 75. All right. So we have a sorted list. I need to look at some element and compare 75 to that element. I need to start somewhere, right? In linear search, the way it works, we would compare 75 to the first element, first to the 2, then to the 3, then to the 4, then to the 9, and so on. Okay, so now that I know the data is sorted, what should I compare 75 to? Where should I go?
71.
You can't see the data. This is hidden from you, right? Imagine you don't know this. All you know is these positions. You're given a list, right? A computer has to read something. Like if you tell it L of 10 or L of 0, it has to go there and read and compare it to 75. So imagine that actually the list is hidden from you. All you see is this position 0, 1, 2, 3, all the way up to 16. Linear search is going to say read first L of 0 and compare to 75. So it's going to compare 2 to 75, then read L of 1 and so on. So that was when we didn't know the data is sorted. Now that we know that data is sorted, what's the first element you would compare 75 to?
You start at 8?
L of 0 or what? Go ahead.
We start at the middle.
We start at the middle. Okay, so let's see why. So we have elements in position 0, 1, 2, 3, all the way up to 16. So we have, Mait, can you put your hand down? All the way to 16. So we have 17 elements. When the number of elements is odd, there is one middle. In this case, it's this position 8. So we read L of 8. Okay, so that's 69. So we compare 75 to 69. All right, so 75 is bigger than 69, and we know our list is sorted. Should I ever read these elements to the left of 69? Should I ever compare now 75 to any element? Now that I found out the 75 is bigger than the element in the middle, should I ever read anything to the left of this middle element?
No.
No, we know already that 75, if it's in this list, for sure it's not to the left, because all of them are smaller than 75. So what that means, with one comparison, we went to the middle, with one comparison, we eliminated half of the possibilities. Okay, we know we did one operation and we now know half of the list is out the window as a possibility. Okay, so we know that 75 is none of these positions. So this leaves as possibilities this type of a sublist, this part of the sublist, right? So the possible places are from 9 to 16. So what should I compare 75 to next?
The middle again.
The middle of the
position
middle.
11.
Exactly, the middle of this new sublist, right? So what does it mean when we look at what are the possible positions left? What we have left actually is another list, now a shorter list, half of the size of the original list. All right, so this is the same problem. I have a list that I know is sorted. We didn't touch it, it's still sorted. I go to the middle, right? This list has 8 elements. Or how many? Is it 8? Or is it, yeah, this list has 8 elements. So it has 2 middles, right? 4th and 5th element of the list is middle. You can pick any one of the 2 and go to them, right? So I'm gonna pick the 4th one of these, right? So that's a 12. I'm gonna pick the of the 2, the slides pick that one. So we go to position 12, so middle of that list, compare 75 to that. 75 is less than 85. So we should never check to the right of 85 because everything to the right of 85 is bigger than 85 and therefore bigger than 75. So we eliminate now half of this current new list. So with one comparisons, we eliminated half of the position. With the second comparison, we eliminated half of the new list. Okay, so the current list where we're looking for this element now is this one here, and it has length 3. What do? You go to the middle. Well, the position 10 is the only middle. And we were lucky at that position, we have element 75 and we're looking for 75 so we can stop at return true. Okay, so let's look at another example where actually just to understand what happens when you don't find the element. How do we figure out that we are done searching? Before we do that, when you compare this, I hope you notice we did only 3 comparisons. We first compare 75 to 69, then we compare it to 85, and then we compare it to 75. So we did 3 comparisons on a list with 17 elements. Whereas linear search did it would compare 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It should be 11 here, not 12. Okay, so we're looking at, even on a small list like this, we're looking at 3 versus 11 comparisons. Okay, so suppose we're looking for 45. So let's have the list again. We go to the middle, position 8. 45 is less than 69. So we should go to the left and eliminate everything to the right. Now we have this sublist as a problem. So current list has 1, 2, 3, 4, 5, 6, 7, 8 elements again. It has 2 middles, the position 3 and position 4. Let's go to the first one. It's a 9. 45 is bigger than 9. So we certainly shouldn't go to the left. We end up with this sublist of 4 elements. It has 4 elements, therefore it has 2 middles, second element and third element. It doesn't matter which one we go to, so let's go to the first. 45 is bigger than 39, so certainly we shouldn't go to the left, we should go to the right. Now we have a list with 2 elements. It has 2 middles, both of them are middle, the first and the second, so let's look at the first. It's 40, so 45 is bigger than 40, so we should go to the right. So we go to the right, we end up with a list of size 1, and middle of that list is just that element. We compare 55 and 45, and we realize that 45 is less than 55, which means we should go to the left, but there's no more left. We end up with a list of size 0 and we are done. So we exhausted, although we didn't read all the elements, it's not even close. We exhausted all the possibilities and we can conclude that the element is not there. All right, so that's this algorithm. First of all, it has a name, it's a famous algorithm. It's called binary search. And it's one of the most famous algorithms on the planet. And we're going to see how good it is. Is it really that much better, or is it better at all in terms of big O notation than the linear search? But before we do that, before we do analysis, let's try to implement this, because this one is not as obvious how to implement this as linear search. Okay, before we do that, let's see what are the critical parts of this algorithm. So notice that we were saying these type of things, go to the middle. So that means I should be able to compute the middle. What's the middle position of a current list? Another thing that we were saying is a current list or current sublist. So we have to keep track where a current sublist, so the list of possibilities, where does it start and where does it end? Okay, so let's go to my next slide. Oh yeah, so here there were 5 comparisons done by binary search and it would have been 17. So linear search always reads all the elements of the list in case the element is not there and ends up reading everything. Okay, so let's go to the implementation. So right now, just look at, just look at this part here, the top. You have this rectangle. Inside of this top rectangle, you have the elements of the list. Above it is indices of this list. Okay, so remember what we have to do. We have to be able to track where is the current list in which we are still searching, which is still where we can still possibly find the list. So we need to know where's the beginning of that list and where is the end of that list. All right. So at the very beginning, we are working, remember the step 1, we were working with the whole list. Okay, so the first thing was you have a whole list and you go to the middle of that whole list. So in step 1, the beginning of the list, so the way you can track what is your current list is simply to have 2 variables, one called B and one called E, that keep track where is the beginning of your list, what is the index of the beginning of your list, and what's the index of the end of your list, your sublist. Okay, so in the beginning, we are working with a whole list. So variable B telling me where is the beginning of the current list should be set to 0, like in this picture. So the beginning of the list is at index 0 of my given list. And the end of the list is at index 12 of the list. And more generally, if you have a list L, the last index is at position len of L -1. Okay, so we know that we do that our list is between positions given by variable B and given by variable E. At the beginning, B is 0 and E in our example is 12. All right, so what was the next step? Next step was, okay, go to the middle index. So that means we better know how to compute this middle index. Okay, so how do we compute this mid position? So I should have a variable mid that, for example, in this first case should give me 6 because that's the middle of my current list. So how do I compute mid?
Len
No.
divided
E
by
plus
two.
E divided by
Integer
divided by
division.
Okay,
Integer
can you
division
raise a
too.
hand? Too many people. Let's raise a hand. Maid was first.
So len of L integer division 2.
Okay, but I wanted later on, beginning and end of the list will not be 0 and len of L anymore. It's going to be something else, right? So how do I compute the middle of the list given B and E? What about Juan?
B plus E divided by 2.
Exactly, integer division 2, because we definitely don't want, in this case, for example, 0 plus 5 divided by 2 is 2.5. We don't want that. So integer division 2. So you do B plus E, integer division 2. Okay, so in this particular example here, we have B plus E is 12, divided by 2 is 6. We go in the first step, we go position 6. Let's say we are looking here, says key, we're looking for 11. Remember, key is another way to say value that you're looking for. And so we compute it. So that's the first thing. We compute a mid, that's B plus E integer division 2. It gives us 6. So we go to this position 6, we read what's there, L of in our list in position 6 is 50. We compare it to what we're looking for. It's 11. 11 is less than 50. So the sublist we should look for 11 to is to the left of 50, right? So we are never going to look to the right. So it's to the left of 50. So now I should update where my lists begin and end. So what should I change? Now that I know that my current sublist is to the left of 50, what should I update?
The B and the E.
B and E, but in fact, B didn't change with this, right? It's the end of the list that should move where? So what should I update E to, end of the list?
E equals mid.
Why mid? We know that 11 is not in mid. We didn't find 11, otherwise we just stop, right?
Mid -1.
-1.
Exactly. So it's we update, if we have to go to the left, we update E to mid -1. Okay, so that's what happened here. So now our current list, beginning of our current list is at position 0 and is at position 5 or index 5 of the list. All right, so we repeat the algorithm. We now have exactly the same algorithm on this sublist. We go to the middle and we now know how to compute the middle. It's b plus c divided by 2. That's 5 plus 0 plus 5. That's 5. Integer division 2 is 2. So we go to that position. We read what's there. And it's a 7. 11 is bigger than 7. Okay. And it's not equal to 7. So we shouldn't stop. We should repeat. So we should go to the right of 7. So our current sublist should change to start after this position, to the right of 7. So what should I update?
B is equal to mid plus 1.
That's correct. So we update b is equal to mid plus 1. We end up in this situation. B is now 3, 4, 5. The middle, so now we repeat again the same algorithm. You have, as long as you have any elements in the sublist left, you continue, or as long as you don't find it. So b plus e here is 3 plus 5 is 8, divided by 2 is 4. We go to the middle, index 4. We find element 11 there. We compare it to what we're looking for. Bingo, we find 11, and we can stop. We can even report that we found it at position 4. Okay, so when does this proceed? How does this, let's first of all, before we code it, one more example where we see what happens, what does this look like? When do I stop if I don't find the element there? Okay, so let's look at that example. We're looking for 54. Again, I start at the beginning. List starts at index 0, ends at index 12. So mid is 12. I'm looking for 54. At position 6, I find 50. 54 is bigger than 50. So we have to go to the right. Therefore, what we need to update, we said, because we need to update where does the list begin. It now begins at mid plus 1, so it begins at position 7. So now I have this sublist as a list of possibilities. So I do 7 plus 12, that's 19. Integer division 2, that's a 9. That's the middle of this new list, sublist. I go to that position, I find 66 there, and I'm looking to 54. 54 is less than 66. So I should go to the left of 9. Okay, so in other words, I should update E to mid minus 1, which is going to be 9 minus 1, that's 8. So beginning, so now I end up with a list with 2 positions. 7, beginning of the list is a 7, end of the list is position 8. We still compute the mid in the same way. 7 plus 8, that's 15. Integer division 2, that's a 7. So mid is in this position. What do we have in mid? It's 59. 54 is less than 59. So remember, when you find something that is less than a middle, you should go to the left. When you go to the left, you should update E to mid minus 1. So we get 7 minus 1. We get that E should point to 6. So what did we get here? We got that the end of the list comes before beginning of the list. All that means is that you ran out of possibilities. Okay, so you can stop. All right, so you, at the beginning, you have a, oh, you can't see both. This is, ooh, okay. In the beginning, you have some list of certain size, and beginning and end. As your program, as your algorithm progresses, beginning and end getting closer and closer. And if the element is not there, eventually they're going to do this, and you know you ran out of possibilities, and you can stop. Okay. So now that we have a plan of how to implement a conceptual algorithm, we can code it. And you will see that now that we have a plan like this, is actually easy to implement. So this is something that you should do yourself whenever you're trying to solve this. Spend some time on a paper trying to figure out what you need to, first of all, to find a solution like a binary search, an algorithm, then what you need to implement it, how would you implement it before you just start coding. All right, so let's code this binary search. Let's see, where is my, okay. So now that we know the name of the algorithm, binary search, All right, we have a given list, we have a value that we're looking for. Very importantly, what we also have is that, unlike in linear search, we have a precondition, meaning this algorithm is only correct if the data is sorted, okay? If you don't give me sorted data, I think I'm gonna give you likely very completely wrong solution to this algorithm, okay? So, well, it's not gonna be wrong if I find it. If I bump into it, said it's here, it's not wrong. But if I say, no, it's not there, it's very likely that it's incorrect, your solution. So with precondition, remember, is when we are saying, I'm gonna give you correct solution under the conditions that your list is sorted, okay? L is sorted from largest to, sorry, from smallest to largest. Okay, so that's a precondition. By the way, notice something here that, and in a way that's a precondition, but in fact it's implied by the fact that data is sorted, that it can be sorted. What you know about list L is that every pair of elements is comparable. What does that mean? The only time you can sort something is when every pair of elements is comparable. Okay, so here let's look at example like this. If I have a list and the elements of this list are 100, and then I have today, and then I have, I don't know, true. This list cannot be sorted. The reason this cannot be sorted is that these elements are not all comparable. What does it mean to say is 100 less than today? This is meaningless, okay? So let's try to do this. Is 100, you are asking is 100, pardon, sorry, 100 less than today, you're going to get an error. This is not supported operations because integers and strings are not comparable. Okay, so by the mere fact that the list that is given to you is sorted, this means that all the elements in the list are comparable, meaning it makes sense that they can be compared. All right, so your list can be a list of numbers because every pair of them can be compared. It's meaningful to us, is this number less than this number? It can also be a list of strings where all the elements are strings. Because if you have a list where strings are ordered alphabetically, meaning any pair of strings can be compared. You are comparing them alphabetically. Let's say albatross versus, I don't know, today. And it's true because A comes alphabetically before T, you can compare strings. Okay, that was not restriction in linear search. Okay, why? Because I can just be checking. If I have a list like this, let's say I'm looking for 100, it's not a problem. We can even see it here because you're just asking, are they the same? You're using equal, you're not using less than equal. So, oh, but I didn't run, this is a, I didn't run this. This is a separate terminal. But the point is that let's say we are looking for 100, I can, let's say we are looking for a 5, I can ask, is 5 equal today? That's not going to give us a problem. We're not going to have a crash, okay? Yes, Maid. Did you have a, okay.
Sorry, that was from before.
No problem. So let's code this, all right? So this is just to understand what are we working with. It's we have a really sorted list, which implies that all the elements in the list are pairwise. Each pair is comparable. Okay, so let's code this. Let's go back to our example. What did we say first? First, we said that the beginning of the list, B is 0 and E is len of L minus 1. So B is 0, E at the very beginning is len of L minus 1. Okay, so And then the rest of the steps we were just repeating, right? So what are the steps that we were repeating? So first of all, we'll be repeating, I'll get to you in a minute, Francois. While, and we need to have some condition here. We have to figure out how long will I be repeating this algorithm. But what was the algorithm? So the algorithm was what we were doing. There were really 3 steps that we were repeating, or 2 if you like. We were computing the middle. Middle was B plus E, integer division 2. We needed to know where is the middle. Okay, now that we know where the middle of the list L is, we were saying, okay, if our first example was if the value V was strictly bigger than the element in position mid, the element in the middle of the list. In that case, we were, first I had, okay, let's say it was this, all right? That value V was less than a middle, then we had to update the end of the list to mid minus 1. So because we are looking to the left, we know that the value V, if it exists, is to the left of that middle element. So in that case, we are updating the end of the list to mid minus 1. Okay, so else if the other possibility is that V is bigger than L of mid. In that case, we have to look to the right of the middle position. So therefore, we have to change the beginning of the list to mid plus 1. So exactly 1 after the middle. And finally, if the element is neither less than the middle element nor bigger than the middle element, well, that means that V is equal to the middle, okay? And remember what we are returning here. We are returning a position where we found the element. So in else case, we found an element and we should return its position. So what should I put here?
Return mid.
Exactly, because we found an element in position mid and we found it and we return it. Okay, so we should be repeating this algorithm as long as our list has at least 1 element, right? Our sublist that we're looking at. So what should I put here as a condition?
Len of L is bigger than 1.
Sorry?
Len of
Remember,
L is
not
greater
len of
than
L. We are
1.
not working with the whole list L. We are working with the sublists that start at position B and end in position E. Kasim.
While B is less than or equal to E.
Exactly. As long as B, beginning of the list, comes before or equal to the end of the list, that means we still have a sublist of a size bigger than 0. Okay, so there is still a place to look at. So we should repeat our algorithm as long as the sublist we are looking at has at least 1 element. And when is that true? When B is less than or equal to E. Otherwise, if there were cross, as we have seen, so meaning we are ending up at least with 0 elements, and we find ourselves outside of the loop, we can safely conclude that the element is not there, and a convention is that we should return -1. All right, so that's implementation of that algorithm. So let's see, let's run it actually to make sure that it's working, at least on some example. So I ran that, and let's try something like binary search, and the list is, it has to be sorted. I don't know, 20, 10, 15.4, 100, 130, something like that. And let's say I'm looking for 100. Okay, and it tells me, yes, that element is there in position 2, so 0, 1, 2, that's correct. Let's see, let me look for something that is not there, 50, and tells me -1, the element is not there. All right, so this solution. We have a solution. It seems to be correct. By the way, I hope you see now that if you spend some time thinking about how to solve it, that coding, it was actually very simple. It may not have been as obvious when you just heard an algorithm idea. All right, so we're looking here at this solution, and as usual, we are assuming that the length, not assuming, but yes, Matthew.
I was just wondering if -1 is a choice or is it a convention?
It's a convention. It's a
Okay.
convention. Especially, and it comes from other programming languages where position -1 doesn't exist. Position 0 exists in every list and positive. So you can always have position that are 0 and positive in lists. But in all the other languages, other than Python, there is no negative position in the list. By returning -1, you're indicating that there is no, that the element is not there, and that's a convention. Okay, Bruno, yes.
Yes, why did we start with length -1?
Because remember that positions in the lists, the first position in the list is 0, and the last position in the list is index len of L -1.
Oh yes, oh I forgot. Yes, thanks.
No problem.
Thanks.
No problem. Okay, so let's see, is this solution, how good is this solution? Bruno, can you put your hand down just so I noticed when somebody, when there's new question? Thank you. So let's see, how good is this solution? All right, so we have a list of size n, and let's figure out how many operations does this solution do. Let's first of all, okay, setting a variable b to 0, that's one operation. This one, setting variable e to, it was 12 in our example, that's one operation. Let's skip the loop, we're gonna figure that out. So here, this line, okay, you can say it's 2 operations. We had 2 numbers, then we divide by 2, let's put 2, not that it matters. Remember that we ignore the constants at the end anyways. I'll get to Francois. And this line is comparing 2 numbers, so that's, let's say that's one operation. This line is reducing some value by 1, that's one operation. This is comparing 2 numbers, that's one operation. This is adding 1 to some number, that's one operation. This is returning 1 value, this is at most 1, because we don't know if we ever gonna do this line, and this here is also at most 1. So inside, so what are the operations outside of the loop? They're only done once. So we have 1 + 1 + 1, at most 3, okay? So what we have here, for these things, we have 3, okay? Inside of the loop, the number of, once we enter, so in one iteration of the loop, in one execution of the loop, we do at most 2 + 1 + 1 + 1 + 1 + 1. So that's 1, 2, 3, 4, 5, 7 at most. What we're interested really, I want to guarantee, right? So at most 7 operation in one execution of the loop. So our whole algorithm does 3 + 7 times number of times this loop is executed. Okay, so each time we execute a loop, we do roughly 7 operations. So the total running time of the algorithm is number of times the loop is executed. Okay, and remember, we are actually going to delete these 3 and 7. So all you care about, so actually this is big O of the number of time the loop is executed, right? So what we have to figure out, the running time of this algorithm is exactly the number of time the loop is executed, okay? All right, so try to enter this for yourself. How many times is this loop executed? Francois, did you have a question while people think?
Yes, my question is, how do we know that the len of L, the function len of L only gives takes one operation?
To find out how many, basically Python just stores the size of the list and you're just reading one value. That's most, well, at least that's most likely way to implement this. But to find out how it's a good question because it's a function call, but it really is just returning you one value that is stored somewhere. So it's really one operation. But if you are wondering, you can just Google a running time of Python operation. You're going to get a list. It's going to tell you how much they cost. Because, for example, that in and that index, as we said, it's linear. Yeah, but it's a good question. This one is, this function is really just reading, returning one value that it stores somewhere. So it's one operation.
Okay, thank you.
No worries. So, all right. So what we have to figure out, how good our solution, we need to be able to figure out how many times is this loop executed. So, Lilia.
Is it log 2 of length of L? Because it's about how many times we can divide until we get 1.
Exactly, exactly. So the answer is, so here, the number of times this loop is executed is at most log base 2 of n. So when you remove these constants, you end up with O of log n. All right, so I hope, as Lilia has told us, that this reminded you of the end of the last lecture, where we saw exactly this type of behavior of the loop. So let's see, when we go to last lecture, there was, maybe I already have this open. I do, from the last class. Okay, here it is. Remember that last mystery function that we analyzed in the last class, I was asking exactly that question, that you're starting with some value n, some integer n. Every time you enter the loop, n gets divided by 2. Next time you enter the loop, n is half of the previous value. Next time you enter a loop, n is half of the previous value, right? So every time you enter the loop, the current value n gets divided by 2. And the question is, how many times can this happen before you get something less than equal to 1? And the answer was log base 2 of n. All right, so let's look at this solution. All right, so we're saying that what's happening in this loop, all right, is the same. Something gets halved every time we enter the loop. All right, so what gets halved here? Not that we are halving it ourselves, but something gets halved and makes the loop end. What gets halved every time we enter this loop?
B plus E.
Is that true? B
The
plus
remaining
E,
list.
we can end up in the middle, right? And middle is n over 2 plus n over 2, and not really. What gets halved?
Is it E?
The remaining list.
The remaining list, right? The length of the remaining list, in fact, E minus B, then it is, because every time you enter, remember, every time we go to the middle, we eliminate half of the current list. So when we look in the sublist, in every time we enter the loop, sublist is half of the previous iteration of the loop. So we start with a list of size n. Next time we enter the loop, the list has size at most n over 2. Next time we enter the loop, the list has size at most half of that. It was n over 2, so it means now it's going to be n over 4. Next time we enter the loop, the list is going to be half of that, half of the previous. Previous was n over 4, so divide by 2 is n over 8. So what we are doing, every time we entering the loop, the length of the sublist is at most half of the previous sublist, okay? Or in other words, E minus B halves, okay? So that's which basically E minus B is length of our list. That's the reason, and that's a definition of the log. How many times can you divide n by 2 before you get something less than equal to 1? And we are exactly stopping when the list is less than equal to 1, right? You start with some list and then you're going to leave the loop after that you get something less than equal to 1. So this solution is log base 2 of n. And so where am I here? Let me show you how much better that is than O of n. Dramatically, beautifully smaller. So let's say we are working with, in the first case, let's say you have a list with billion elements. Linear search is going to do billion operations, and binary search is going to do roughly log of a billion operations. We do have this time 7 times 3, but roughly. So math.log, we are asking billion, that's 9 zeros, 1, 2, 3, 1, 2, 3, 1, 2, 3, base 2, about 30 operations, okay? So we are comparing billion to 30s, but let's do, what about if the list has billion of billion elements? The linear search is going to do billion of billion operations, whatever that means. I mean, what I mean is 1 followed by 8%, 1 followed by 18 zeros. So linear search is going to do that, and you're going to wait forever, well, forever, months. But let's see. The binary search is going to do roughly log of 1, and what did we say? 0, number of 0 is 8, 9 plus 9, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, base 2. Look at that, 63, okay? It's going to do on a list of billion elements, it's going to do only roughly, let's say, rounded up 64 comparisons. So, and remember, your computer can do about 1 million operations a second, and this is absolutely wonderful, and there is a reason this algorithm is so famous. It's used everywhere, even in places that you wouldn't expect. As I mentioned before, for example, it's used in an implementation of your browser. Your browser is doing, I don't mean in search, in your actual in Chrome. Chrome is performing these operations all the time. All right, so that's what I wanted to show you about binary search. But actually, there is something else I wanted to show you. How much time do I have? Yeah, here. Let me show you something. I'll go back here. So when I have a list, oh, by the way, just to demonstrate that this solution works on the strings. It doesn't have to be, as I said, as long as what you're working with is sorted and comparable, this is binary search works. So it could be that you have a list like this. What was my examples? Albatross, bat, today, ZZ, I don't know if that's a word. I don't know why I put that, because I can't come up with any, oh, 0, for example, something like this. All right, so we have a list of strings. They're alphabetically sorted or lexicographically sorted. And if I ask, I can call my binary search, because all I'm doing is comparison and comparing things that are comparable. I can say in this list L is a word 0 there, and tell me yes, and it's in position 3 of the list. I can ask, is a word glasses there, and it tells me -1, it's not there. All right, but here's another example that I wanted to show you about this topic. Let's say I have something like 2 and 30, and then 20, oh, sorry, that has to be sorted, 44, 44, 44, 44, 44, 44, 44, 44, 44, I don't know, 100, 100, I don't know, that's it, that's enough. All right, so I have a list, it's sorted. And I'm asking, so we call our binary search again on this list L, and I'm looking not for glassing, I wanna know, is 44 there? 44, is it there? Tells me yes, but notice something, compare this to index implementation of Python. When I'm asking in this list L, is 44 there? It tells me yes, and it's in position 2. This one tells me yes, and it returns the position 0, 1, 2, 3, 4, 5, 6, this one. Okay, this position, and index returns this position. In other words, index returns if the element is there, it returns the first occurrence of the element in the list. In our case, if the element is there, we return a position of where we can find this element. Okay, so this may be what you want, so it's fine. But it may be that actually, oh, I want my binary search also to return the first position that a given element exists in, if it's there. All right, so how would you modify your binary search to achieve that? So it returned this one, and it should be clear why, you know, remember our algorithm says go to the middle. In this case, if you go to middle, you immediately find 44 and you report this position.
Once you find the right index, then you compare it to all the index before, and if they're equal, you return the last one. If they're not, well, yeah, once you find an index that is not equal, you return that one.
Okay, so that's a correct solution. The solution is the following. So let's say in this case, it was found in position 6. So 0, 1, 2, 3, 4, 5, 6. It was found here. And you want to find the first one, and you go to the left, until as long as you're still seeing 44. So we go to the left, it's still 44. We go to the left, still 44. To the left, still 44. To the left, still 44. Okay. I go to the left now, it's 30. Okay, that means this is because it's sorted. This position is a first occurrence of 44. That's a correct solution. But is it still log n solution?
Nope.
No, it's not. We could have a whole list of billion elements and they're all 44. You go to the middle, you find it in 500 million position, and then you have to read everything all the way to the first position to figure out where is the first 44. Okay, so
I have a proposal. Maybe
sure.
we can, where you wrote as return mid, we don't do that. We let the whole algorithm run,
exactly.
and then
not whole. You still have to figure out that. So the idea actually, how, and you're going to have to do this for your lab to modify this so it works with this. And the idea is actually that you can still continue the algorithm, right? You go to the middle of this, and the 44 is still there, but you certainly shouldn't go to the right, because then the first 44 have to be to the left. So you go to the middle of what remains. If 44 is there, you repeat on the left. If 44 is not there, you know the first one has to be to the right. So you do go to the middle of the right. So it's the same solution. And by the way, this is a common interview question where the students or whoever is being interviewed doesn't necessarily recognize that this is application of binary search. So here's the problem that you're gonna hear. It's, they're gonna ask you, okay, here's a list, and a list has only zeros and ones, but you, let's say, million zeros in one, but all the zeros come before all the ones. So you have 0, 0, 0, 0, 0, 0, and then you have at some point 1, and then you have ones to the end, 1, 1, 1, 1 to the end. So the question is, design an algorithm that reports where is the first one. Okay, so you can do a trivial one, or read the first element is 0, read the second is 0, read the third is 0, and you go on until you bump into 1. That's not what they want. Okay, so this is also where you should think of binary search. You go to the middle. If 0 is in the middle, but certainly 1 is to the right, there's no point going to the left. If the 1 is in the middle, you go to the left, and then you repeat. So this is also, it's just binary search. Okay, all right. So the last thing I'm going to show is a different problem in the last 6-7 minutes. And the problem is, I want you to, given a list, so input given a list of comparable elements, given a list, I want you to report or return k largest. So you're given a list and you give an integer k, a positive integer. I want you to return k largest elements from L. Okay. So if you have a list of numbers, when k is 1, I'm just asking what is the maximum in the list, right? I'm asking for the one largest element. If the list is, let's look at the example, 2, 3, minus 100, minus 20, minus 32, and 55. Okay, I have a list like this, not necessarily sorted. I'm asking you, when k is 1, I'm returning one largest element from the list, it's 100. When k is 2, I'm asking for the two largest element in the list, that's 155. When k is 3, I'm going to return three largest elements in the list, so that's 100, that's a 55, that's a 3, okay? Okay, so these are, and so on. I hope you understand the problem, right? You give me a list, you give me an integer k, k is at least 1 and at most number of elements in the list, because otherwise it doesn't make any sense. And I want you to return a list containing k largest elements of the given list. Okay, I'm going to propose two solutions, both correct, but let's figure out which one's better. All right, so I'm looking at algorithm 1. First solution. Step 1 of the first solution, sort L. So now L is sorted, and you just do return plus k elements. That's the correct solution. They're going to be the largest k. In fact, this last line is particularly easy in Python to implement. You just do return L starting at position minus k, you do slicing to the end, right? So this actually returns, this line returns last k elements of a list L. Okay, so that's algorithm 1. Algorithm 2. 2 goes as follows. I say repeat the following k times. Repeat k times the following. What do we repeat? First, I find the max in L. All right. I find the max. I add that max to the list results. And finally, I delete that maximum from L. Okay. So I find a maximum, I put it in my list of results, and I delete it from L, right? Such that I don't report the same element again. Then I find a maximum again now in this list and delete it, I do this k times. So at the end, the elements that I deleted from the list and put from the result, they were the maximum. Okay, so both of these solutions are correct. Which one is better in terms of number of operations?
First one.
Okay, we have one vote for the first one. Anybody else?
First one.
Thanks. The first one.
3 votes for the first one. Anybody else?
Actually, there's another operation we need to do in the algorithm 2. We need to return the list results.
Sure, yeah. Yeah, that's not in both of them. We need to return, yeah. Return the list results, yeah. It doesn't make much difference in terms, but yes, we do have to, you're right.
The second one?
Okay, so we have a vote for the second one. Okay, so.
I say the second one is.
Sorry?
The second one.
Okay, another vote for second one. So we have a split vote between first and second. And so in order to actually determine that, we should do analysis. So let's do this next in the last couple of minutes of the class. But let me say that each group is both correct and both wrong, depending on we'll see what, right? In some situation, algorithm 1 is going to be better. In some situation, algorithm 2 is going to be better. To understand this, let's analyze these algorithms. So this one literally has 2 lines. Sort L. L has n elements always for me. So this costs us big O of n times log n operations. So that's line 1 is this many operation. Line 2 returns k numbers. In order to return k numbers, one can argue that you have to read them. Although you can just return a pointer to the second to last element, but let's say you have to read them, doesn't make much difference. If you're reading k elements, let's say that's k operations. Okay, so the solution is n log n plus k. All right, so algorithm 1 does k plus n log n operations roughly. Remember, we really want an upper bound. I want to say, I guarantee that my solution will do at most this many solutions. Well, k is at most n, right? I can ask for at most n maximum values. So this is at most n plus n log. So the other one I just copy, n log n. Well, remember, in big O notation, just keep the faster growing, the one that gives you more operation, and certainly n log n gives you more operation than n here. So this is big O, this solution is big O of n log n. Okay, so that's our analysis of solution 1. Let's look at analysis of solution 2. Every time, so we're going to repeat the loop k times. So let's see how many operations do we do in a loop. Find the max. We've done this. You go through the list once and keep track what's the max. So when you execute this once, you do O of n operations. Okay, linear number operation is that line. Add that maximum to the list of results. You can append, that's one operation. Delete that max from the list. By the way, you may be tempted to think that deleting is a constant because adding is a constant. But adding, you add it to the end of the list. You may be deleting something from the middle of the list. So you're calling a Python function that deletes something from a list. You may think, oh, what's the big deal? I just delete. But one of the crucial properties of the lists, and one of the things that makes lists fast, the main property of the list that you're using all the time is that accessing, if you give me an index, accessing that element in that index is a constant number operation. The only reason that's possible is because elements of the list are consecutive in the memory, okay? So if I know the beginning of the list and you say I want 100 elements, you know exactly I jump 100 over and I'm going to read in 1 or 2 operations, I'm gonna go to the 100th element. If the elements are not consecutive, if you have holes in between, you don't know, have no idea where's that 100th element. So when you delete something, you're creating a hole, you may have to move half of the, if you delete a middle element, you'll have to move half of the elements to the left. So what's hidden from you is that delete is actually linear number operations in the worst case. So you may be doing linear number operations here, return the list of k elements as before, let's say that's k operations. Okay, so that's one iteration of the loop and we do it k times. So inside of the loop, we are doing n and 2 times n plus k times k. Okay, so what we end up here with is roughly k times, because we repeated the loop k times 2n plus k. Okay, again, k is at most n. So you can say that this is at most k times 2n plus n. So this is at most 3k n. So since we're removing a constants, we have that this solution is roughly k times n. Okay, so now we can compare these two solutions. When is one better than the other? Let's say k is 1. Well, if k is 1, this one is linear, and this one is not. It's n log n, it's worse. If k is 2, I'm going to get you, Maid. If k is 2, this one is 2n, that's still kind of linear, right? You can just compare these two equations. When is kn smaller, less operation than n times log n? It's probably easier to see if you write this, if I write this as n times k, n times k. So here, the first term is the same, n times. So when is the second one better? Well, when k is less than log n, the second one is better. When is the first one better? Well, the first one is better when k is bigger than log n. Let's say k is n over 2. We get here n times n over 2, that's n squared over 2, that's roughly n squared, okay? And when k is roughly log n, they are the same, okay? So when k is asymptotically much smaller than log n, the second solution is better. An example of that, if k is 1, right? You're returning just one maximum, then the second solution is better. Just find maximum, forget sorting. And when k is much bigger than log n, then the first solution is better. So that's all for the lecture today. I'm going to take some questions now. Maid was first.